Hello and welcome to episode 19 of How to Code Games in BBC Basic. In this video we're going to be looking at collision detection. So in our last video we were looking specifically at missile mechanics and in particular the procedure move missile, which we went into the details of. But in that video I highlighted the fact that there is a call to a function called fn find char, which you can see here at line 1590. And we skipped over that one, and I did say that we would look at it in a future video. Well, this is the video in which we're going to look at it. Now, a word of warning, this is likely to be the most complex of the topics that we've covered in this series so far, and the reason being it actually slightly delves into the realm of machine code. Now, when I say that, I don't mean that the program itself contains any machine code directly. Everything in this particular program, Cosmic Invaders, is written in BBC Basic, but it makes use of machine code by effectively calling a predefined machine code routine. So to make sense of how this particular function is working, we are going to have to touch on a few topics that relate to machine code, but I'm going to try and take this nice and slowly, and hopefully it will all make sense in the end. So here we are at the function itself, fn find char, and the purpose behind this function, as we highlighted in the last video, is effectively trying to tell us whether or not there is something on the screen at the current print cursor. So if we pop back again to our move missile proc, you will notice that before we call the function, we have this print tab command that doesn't actually print anything, and that's important because what it's doing is it's setting the x and y coordinates of where we would like to print our next missile, which would be the position of the missile as it moves up the screen into its next position. But before doing that, it wants to know whether there's actually anything already in that position on the screen. So we set the print tab using the x and y coordinates here, but we don't actually print anything. By putting that semicolon at the end, it simply says, as and when the next print is called, it will be printed at that position, and that's sufficient for the purposes of this function, because what this function does is it then says, okay, well, at that location where the print cursor is currently sitting, is there a character on the screen or not? But how is it actually doing that? If you actually look at the function, the actual code is relatively short. It's just three very short lines here, the third line of which is simply returning a value back to the bit of the code that called the function. So it doesn't really seem to be doing very much at all. And for something that's quite as advanced as being able to say what is on the screen at a given location, you would expect to see more code. Well, the reason for that, as I said earlier, is that actually what's happening here is we're simply making a call to a predefined operating system machine code procedure or function. But it's still not very clear exactly how that's working in practice, so we need to unpack this slightly. So I suppose the first thing to say is that we are making use of this uppercase C, lowercase h percentage variable. We haven't really seen that up until now, so what we're going to do is just pop up to the top of the screen of our program, and you'll notice that it actually is sitting there just at the end of our dim command that we had in line 50. Now, in a previous episode of this video series, we talked about the dim command and how it's primarily used for defining arrays, and indeed all of the variables that come before this one you'll notice have got the brackets around a number, and as we said in the previous episode on this topic, this indicates that I want to create an array, and I want that array in this case to have 10 items in it because we index from 0. This one's a bit different because it doesn't look like it is actually an array because it hasn't got any brackets around the 3. Now, you might think, oh, maybe that was a typo in the original program listing, but no, this is entirely correct, and this kind of syntax is perfectly permissible in BBC Basic, but it means something slightly different. So when we declare a dim and we want it to be an array, we obviously use the syntax that you see here for these other variables. But if we use the dim command with the name of a variable and then a number without brackets, it means something slightly different. It means I want to reserve a set number of bytes of memory. That's all it means. And again, we index from 0. So if I say I want to reserve 4 bytes of memory, then I have to declare it as the name of the variable and then a 3. So that's effectively what I'm doing here. If I literally just said dim ch percentage, that would mean I want to reserve 1 byte of memory because I haven't specified a number, so it'll just say, okay, well, it assumes the index of 0, and so you just get 1 byte. But when I put a 3 next to it, it means, okay, I want the 0, 1, 2, and 3 bytes from the starting position of ch percentage to be reserved for me. So that's what the dim command is doing here, is behaving slightly differently from the way that we've seen it used up until now. And indeed, when you do this, you can actually then use, if we go back to our fn find character, you can then use the question mark or the query operator to query a specific one of those bytes that you've reserved. We can see this in practice. It's fairly straightforward to achieve. So if I declare a dim, I'm just going to call it ch with uppercase because it's easier than turning the caps lock on and off. I'm going to declare it in the same way that the program does. So I'm going to say dim ch percentage 3. And you can see that the BBC Micro is, or BBEM in this case, is entirely happy to accept that as a command. And then if I wanted to say, well, what is there? I could say print ch percentage as I would with anything else, but I get a slightly bizarre response because ch percentage actually is not truly a variable. All that I've done at the moment is reserve an area of memory, but I haven't done anything to it. So really what I have to do if I want to print items in that particular area, I have to be specific about what it is I want to look at. So if I do ch percentage question mark 0, now I can see the first byte that I've reserved. And likewise, if I do question mark 1, I can see the second byte, the third byte, and the fourth byte, and we can see that they're all set to 0. So that's essentially how you can understand what is at the memory location that you've reserved. You can't just use it like a conventional variable. It doesn't work that way. You have to instead be specific about the particular byte that you're interested in. And as you can see at the moment, I've reserved 4 bytes of memory, 0, 1, 2, and 3, but I haven't put anything in them yet. So they're all, as you can see, set to 0. Now, if I want to put something in there, I can use a different operator, which is called the exclamation, sometimes known as the bang, or indeed the shriek operator, I've heard it called. And it's an exclamation mark at the end of the day. And what this does is it helps you to specify what you want to put into a memory address. Now, if you've ever used other varieties of BASIC other than BBC BASIC, you may have heard of commands like peek and poke. That's effectively what these question mark and exclamation mark operators are allowing you to do. So the question mark operator works in the same way as a peek, so you can look at a particular byte in memory, and the exclamation mark works similar to the poke command. But the exclamation mark has to be used for 4 bytes of memory at a time. It doesn't work for individual bytes. So if you want to if you want to poke something into memory, you have to work in multiples of 4. Now, conveniently, we've reserved 4 bytes of memory. So what I can say is I want to poke into the memory address that I've reserved a set of values. Now, this actually is done using hexadecimal typically. And in BBC Basic, if you want to specify that the value that you're giving it is in hex rather than in conventional decimal, you just put the ampersand. And then what I could say is, okay, I want to put values of 1, 2, 3, and 4 into my 4 bytes of reserved memory. Now in hexadecimal, provided we keep to these low numbers, anything basically from 9 and below, it works in the same way as decimal. So provided we don't go to a value higher than 9, we don't have to start getting into the slightly peculiar syntax of hex. That's a topic for a totally separate video, perhaps in the future. So anyway, we're going to do that, and you can see that it's happily accepted my command there. So what I'm now going to do is repeat what I did before and say, okay, well now tell me what is in my first byte of reserved memory. It's a value of 4. And if I look at the second byte, it's a value of 3. And if I look at the third byte, it's a value of 2. And if I look at the fourth byte, the value of 1. And you'll already be able to tell that when I use this exclamation mark operator to poke information into a reserved memory address, it works backwards. So the fact that I actually put in 01, 02, 03, 04, when we come to actually retrieve that from memory, you have to remember that the way that this is managed by the BBC Micro is that it actually operates in sort of reverse order from the sort of intuitive way that you might think. But anyway, that's effectively how these two operators work. So if we go back to our function here, what you can see, we'll come back to some of this in a minute, but what you can see at work here is at the top of the program, we said, using the dim command, I want to reserve 4 bytes of memory, indexing from 0, hence the 3. So I've reserved 4 bytes of memory using this CH, oh, my initials, you just noticed that, using this as the designation for where those bytes in memory reside. And then having done that, it means that inside my function here, I can not only use the exclamation mark operator to push something or poke something into that address, into the 4 bytes using the exclamation mark, but I can then also query. In this case, you can see here that the function is actually returning the second of the bytes. So this one is pushing 4 bytes in, and we'll come back to what it's actually pushing in a minute. But here, what it's actually returning, so what the function itself returns, is only one of those 4 bytes. In this case, it's the second of the 4 bytes that it returns. So we've already got a feel for how the function is working. So the proc missile, or sorry, proc move missile, is setting our print tab, saying, okay, set the print cursor to this location. Then it calls this function, and this function returns 1 byte of information. And if that 1 byte happens to be a value of 32, if we go back to move missile again, if it happens to be a value of 32, then all well and good. But if it's not a value of 32, then obviously we go on to call proc hit. So that's effectively collision detection. That's effectively what it's doing. But I suspect that the more curious amongst you will think, well, all right, in theory, that's what the function's doing, but how is it actually doing that? Because we haven't really explained how it does it. We've just said what it does and how it interacts with the rest of the program. Well, if we really want to understand how this is operating in practice, we're going to have to delve a little bit deeper. So the first thing that you're going to notice here is this reference to a percentage. Now, once again, in a previous video, we covered the resident integer variables, and we said that, well, resident integer variables, which you can call from a percentage through to z percentage, in fact, I think there's also an at percentage as well. They're essentially like quick integer values that you can use to speed up your basic program. I didn't really go into any more detail than that, but that's effectively what a resident integer variable is most of the time. But as it turns out, there is something slightly more to them than that. They can also be used as essentially memory address entry locations for predefined machine code. Now, that sentence alone probably needs a little bit of unpacking. So again, we'll take this slowly. So the 6502 processor, 6502 MOS microprocessor that the BBC Micro has, these days you'd probably call it a CPU, but in the days of the Beeb when it was the home microcomputer market, they were referred to as microprocessors. So the 6502 is essentially the brain of the outfit. It is the one that is doing all of the heavy lifting. So even when you're writing a basic program, ultimately what's happening is your basic program is being interpreted by the basic interpreter, and the interpreter turns your basic program into machine code, and the 6502 processor processes the machine code. So if you want to talk to the 6502 directly, not through the medium of BASIC, you have to talk to it in machine code. Now, if you don't want to write machine code, which I did say quite, I stressed at the start of this video series when I began it that we weren't going to cover machine code in this series, and I'm going to stick to that in principle because, as I said before, the program here is not using machine code directly. However, if you want to talk to the 6502 in machine code, but you don't want to write your own machine code, what you can do is make use of predefined machine code routines. Now, what that means is that the 6502 actually has a whole series of pre-written bits of machine code, and they're all basically there within the 6502. And if you know the name of the particular machine code routine you want to run, you can just call it, and it will return back the value that that machine code routine produces. So essentially, it's like a whole library of predefined functions, if you want to think of it like that. It's basically a library of functions, and if there happens to be a function there that achieves what you would like to do, you can just call it. You don't have to know how it works. You don't have to write any of the machine code to do it. All that you actually have to do is say to the BBC Micro, within your basic program, I want to call that machine code routine that's called such and such, and you call it, and it passes a value back to you in the way that indeed our own function is doing here. So when our program calls fn find char, it calls the function and the function returns a value. And actually these operating system machine code routines, or 6502 machine code routines, they work in a very, very similar way. And we can see it at work here. That's actually what this USR function here, that's what this is doing. So USR is, broadly speaking, a BBC Basic function, but it's really shorthand for I would like to call a machine code routine. That's really what USR is. So it's a function that says, like within your basic program, I want to call a machine code routine. Now, the tricky part is to know what machine code routine you actually want to call. And of course here it looks a little bit mysterious because you've got this ampersand FFF4. Now actually that is just a hexadecimal code. It's actually a 2-byte hexadecimal code that refers to a particular named machine code routine. Now we're going to just quickly open up the wonderful Beeb wiki, and you'll see here that OSBYTE, which is the actual sort of, if you like, real world name of a particular machine code routine, OSBYTE itself, you can look down here at the entry points, you can access the OSBYTE machine code routine from address ampersand FFF4. So jumping back to our program again, all that this is saying is I want to call the OSBYTE machine code routine. That's it. It's as simple as that. So this line says, please give me the return value of the OSBYTE machine code routine. And we'll just shorthand refer to it as a machine code function. So I want to call a machine code function, namely FFF4, which is OSBYTE, and I want the returned value of that machine code function to go into these 4 bytes. And that's how you have to interact with machine code functions. They are a little bit different from functions that you might write within a basic program. You can't just pass a variable. You can't just give it a variable and expect it to populate the variable, because variables are essentially BBC Basic variables, and you can't give a BBC Basic variable to a function that is written in machine code. They're incompatible. So the way that you interact with the machine code routine is you give it some bytes of memory. You just say, look, I've got these 4 bytes of memory kicking around here. If I call this machine code routine, please can you just put into those 4 bytes the value that this routine returns. And that's it. So it's a very simple means of calling a predefined operating system routine or machine code routine. Now, it gets one step slightly trickier because we still haven't quite understood what's going on with this A percentage here. Now, the reason for that is actually quite simple in practice. So OSBYTE is a very, very wide-ranging machine code routine. It's actually got lots and lots and lots of varieties. They're called function codes. So OSBYTE is a function, but it has many, 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 many things that it can do. So when you call OSBYTE, you actually have to tell it which particular flavor of OSBYTE do you want to run. And actually that's, again, very similar to certain user-defined functions. Like if you write a function, sometimes, not in the case of this particular function that we've been looking at here, this function you don't actually pass anything in. But if you imagine that, for example, that I actually did have something being passed in here. So perhaps, I don't know, I had this as an input value. Actually, we'll make it more specific. What this would mean, if I'd written the function in this way, and within the function I might have had an if statement that said, I don't know, let's just try and sort of imagine if input percentage equals 1, then da 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 da, else da 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 da, right? So what that would mean is that actually now my function could do 2 different things. If I passed in an input value of 1, then the function would do one thing, but if I passed in a value of something other than 1, it would do something else. That's really all that's happening here with OSBYTE. The only difference is that it's got, well, how many have we got here? 256, bearing in mind we index from 0, 256 different things that it can do. that's really all that this means. So it's not enough to simply call OSBYTE, which is what this is doing. We have to call OSBYTE and then specify what we want OSBYTE to do. And that is what this is doing here. Now it works slightly differently, again, because we're interacting with a machine code routine, but what we're saying here is that I would like OSBYTE to run the, in this case, hexadecimal 87, which in decimal is 135. I want to run the 135th flavor of OSBYTE. And you can see it, again, on the Beeb wiki. If we zoom in a little bit, just to make it a bit easier to read, there you go. You can see that hex 87, or indeed 135, tells us the character at the text cursor. It also tells us the screen mode as well, but this is what we want to know. We specifically want to know what character is currently at our print cursor, or at the text cursor. And really, when you interact with OSBYTE, when you're using the 6502, you just have to use the a percentage resident integer variable as essentially as your input. So whereas when you write a BBC Basic function, you can just say I want, in this case, input percentage to be my input variable. If I then called this function, I'd have to say fn find char brackets and then a value of 1 or 0, let's say. Here it works a bit differently because, again, you're interacting with machine code routines. So what you have to do is essentially put a value into the a percentage resident integer variable of 135, or hex 87. And then when you call OSBYTE here, the first thing it will do is it'll go and look at what's in a percentage, which translates in machine code to something slightly different, but it's effectively a memory address. So OSBYTE will always go and look at what is in that value before it then runs. So of course, if you didn't set anything for a percentage, it would just default to 0, which if we come back here, it'll just tell you, oh, what's the host operating system. In fact, we can see that in practice. If I were to, let's start this again. So if we imagine that instead of having set a percentage, I just literally, let's do a c percentage, dim ch percentage 3, so reserve my 4 bytes, and then just straight away say, okay, put into those 4 bytes OSBYTE. So just call OSBYTE, okay? And there you go. It's told me that my operating system is OS 1.2 because I didn't put a value into a percentage before I called OSBYTE. Now, if I do what this program is doing, so reserve my 4 bytes of memory. Now I'm going to set a percentage to hex 87. Now I'm going to do my call to OSBYTE again. USR, not USSR, obviously. FFF4. And now I say, okay, well, all it's done now, you see, is it's plonked the values into my 4 bytes of memory. And if I do what what the function is doing and query the second byte, ta-da, it's a value of 32. Why is it a value of 32? Well, when I got to the end of this line and hit enter, my print cursor was here on the screen. And there's nothing there, right? There's a space. So I get the value of 32, which is the ASCII value of a space. But actually, I haven't just got that back from OSBYTE, because if you remember from the Beeb wiki, it says it doesn't just tell you that. If I again go and get the third byte from what was returned by OSBYTE, I get a value of 7 because I'm in mode 7. If you don't believe me, let's do it again. So we'll say dim ch percentage 3 to reserve our memory again. Then we're going to set a percentage to hex 87, and then we're going to do our exclamation mark operator to poke the value from OSBYTE FFF4 into memory. Okay. Now if I do my print ch percentage question mark 1, again it's still a space, that hasn't changed, but if I look at the third byte, it's a value of 2 because I'm in mode 2. Anyway, let's get out of mode 2 because it's horrible. Well, it's not horrible, it's great for games, but it is terrible to type in. So we now understand what is happening here within this function. If I just undo some of the mess that I made when I was trying to illustrate how you might do this as a function. So we'll just clear all that up. So we'll go back to how it looked before. So our function, when we call it, the first thing it does is it says, right, I know I'm going to be calling OSBYTE, so I'd better tell OSBYTE which particular bit of OSBYTE I want it to run. And in this case, we want it to run the specific routine that tells us what is at the current print cursor. Having done that, using my previously defined 4 bytes of memory, which I reserved at the start of the program, I then say, okay, poke into that memory location the return value that OSBYTE will give me. Now you might be thinking, well, we've reserved 4 bytes, so does OSBYTE tell us some other stuff as well? Yes, technically speaking it does. It does actually give us 4 bytes of information when we call it. So if we want to know exactly what those are, we will just once again do what we did before. So we're going to do our A percentage here, 87, oops, sorry, that should be ampersand 87, hex 87, and then do our call to OSBYTE, and we'll say, we go ampersand FFF4, okay, and so we've now populated those 4 bytes. So if we want to look at them in sequence, we can just literally go first one, 135. Now 135, interestingly enough, is the decimal value of 87 in hex. So what that means is OSBYTE doesn't just tell us what it's pulled back, it also tells us what we passed in. It's just a way of being able to tell us that, well, you called OSBYTE, and by the way, this is the particular starting memory address within OSBYTE that you told me to run. So it's just essentially like a return value, so you know what you passed in. Obviously, the other values we know already, so the second byte is the space, because that was what was at the print cursor at the time we called it, and then we got the mode, which is mode 7, and then finally we've got the fourth byte, which who knows what that means? Well, what it actually means is it's the carry flag. Now, depending on which particular OSBYTE command you actually ask the 6502 to run, it may or may not make use of a carry flag if it's doing a particular arithmetic operation. That is way beyond the scope of this particular series of videos, but just suffice to say, if you happen to use an OSBYTE command that does some 6502 8-bit arithmetic, it can be important to know whether or not the carry flag was set, and that's what that fourth byte is telling us. We don't care about that for the purposes of Cosmic Invaders. In fact, we only care about this one, the second byte returned. We're not even that interested in what the mode was. We just need to know that in this case it was a space. So hopefully, it's taken us a little while to get there, but hopefully that's made sense now of what this rather cryptic function is doing. We probably could have just left it within the first 5 minutes of this video where I said, this function tells you what's at the print cursor. But, as I say, that doesn't make sense of exactly what the function is doing in practice, and given that the spirit of this video series is about deconstructing a BBC Basic type enlisting, I think it's important to understand exactly what's going on here, and hopefully we've managed to work that one out. So a slightly complex topic for this video. I promise that in the videos to come we won't be going into anything as complicated as this again. This is really the sort of as complex as it gets in this particular program. But I thought it was important to look at, and if you haven't already, do check out my recent video that I did all about memory addresses. You may find that helpful to understand some of what we've covered here today. And in future, I'll also be doing a video tutorial on hexadecimal. So if any of the conversions between hex and decimal have seemed a bit strange, if you're not used to that, I will be hopefully uncovering the mysteries of hex in a future video as well. But for now, I'm going to draw it to a close for this particular episode of How to Code Games in BBC Basic. I hope you found it useful, and I hope you'll join me for the next video in the series. And until then, goodbye.